Welcome, and today we're going to work through a couple problems with reflection and refraction. Quick review of reflection. Angle of incidence in equals angle of incidence out. And remember, if this is your surface, you get a beam of light coming in, it'll bounce out, and you always measure your angle from the normal. This part, 90 degrees right there. Let's work a quick example. You've got a beam of light coming in, hits at an angle of 70 degrees, and then bounces out. And we want to find the angle it bounces out at. So first thing you need to know, you always measure from the normal. That means this is 20, which means this is 20, and you get that this is 70. The other trick to remember is that all the angles in a triangle add up to 180. So 70 plus 80 plus whatever this mystery angle is equals 180 degrees. So your mystery angle equals 30 degrees. So this is 30. So if that's 30, that makes this angle to the normal 60, which makes this 60, which means this angle that you're questioning is in fact 30 degrees as well. And that's the problem. If I were to complicate it, I could add extra things to bounce off of, or you could start trying to figure out the lengths of these sides to a triangle. Now let's talk a little bit about refraction. So refraction is when light bends when it enters a medium with a different index of refraction. This is very important. The index of refraction has to be different. And then a definition for the index of refraction, N, is just speed of light in a vacuum divided by speed of light in the medium. Medium being whatever it travels in. So if we look at this, let's have a ray of light coming in here. Always from the normal, so there's your normal, to this side of the parallelogram. Now, I like to think about this as two little wheels. And going in, you don't have to. This wheel's going to hit first, and it goes slower in here, which means your light beam is going to turn towards the normal. So we'll turn it this way. Oh, and then I hit here on a sketch like this. Okay, good. So now it hits here. This is my angle. It's going to go faster here. Look at these wheels. So this top wheel is going to get outside faster, which means it's going to bend away from the normal. So this angle is smaller than that angle, and let's branch that off kind of that way. And that's how you would sketch this. Here's another example problem, and this one's a little bit different in that you're given an angle and numbers. So to calculate the angle, you will always use Snell's law, N1 sine theta 1 equals N2 sine theta 2. Now you start off in N1, so this is the first side, so you'll be at 2.42 as your index of refraction. Sine 30 degrees equals N2 sine 15 degrees. Do a quick sanity check. Which way did this bend, the light bend here? Towards the normal or away from the normal? And then what does that mean about the index of refraction here? Does that mean it's going to be bigger or smaller? Okay, let's check. After we plug in the numbers, we get N2 is equal to 4.68, which is a bigger index of refraction, and you can tell it's bigger because it's going to bend towards the normal. This wheel gets out first if we draw our little wheel car. I don't know if this helps, but it's how I remember it, so I'll just draw it this way. This wheel hits first, goes slow. This wheel still goes fast, so if this one's going put, 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 and this one's going vroom, it bends towards the normal. One last example is the critical angle. So critical angle, light's going to come in, and at the critical angle, and we'll call this theta c, it skims off the top. So all this person will see is the shore. And this angle, theta 2, is equal to 90 degrees. That is the most important part about a critical angle. If the light came in beyond the critical angle, like this, it would bounce, and you would just view the floor. Maybe that's buried treasure or something there. Who knows? Oh, in that case, you'd want to see it. But I digress. Okay, start with Snell's law, N1 sine theta 1 equals into sine theta 2, where if this is 90 degrees, sine of 90 is just 1. So now we have into equals n1 sine theta critical. Move this around, you get sine theta critical equals n2 over n1, and theta critical equals 56.4 degrees. If your angle of incidence measured from the normal, always from the normal, is bigger than 56.4 degrees, you will see the bottom of the ocean floor. I hope that helps. It's a couple of examples, and I will see you in class.